Growth and decay is a topic that comes up in a lot of different math classes, including algebra, pre-calculus, and calculus. We want to focus on the calculus side of it today. So the rule states if the rate a population changes with respect to time is proportional to the amount present, then we have the differential equation dy dt is equal to k times y. Then the formula for growth and decay is given by y equals ce to the kt. Now, if you recall back to algebra, this formula right here looks like something you learned in algebra, and that is your interest equation, where you had y was equal to pe to the rt. We a lot of times called that the PERT equation, and that's just related to this general equation here. Now, what we want to do is try to figure out, okay, what do all these little pieces mean? So first of all the different variables presented in this problem have a different name. So y is the amount present, and then that amount is whatever relates to the given word problem. T, of course, is time. And then c and k are both something we need to know. K is known as the proportionality constant. This is the constant that tells you how much is proportional to in terms of the amount that we're looking at. C is the initial amount. Now, we do have to notice that that is only the initial amount when we are given dy dt is equal to ky, and we're finding those types of problems. So when they tell you that the rate a population changes, which is that dy dt, is proportional to the amount present, which means k times y, then c would equal the initial amount. But if your differential equation equaled anything other than k times y, it's possible that it's not going to equal the initial amount, because you're going to have to do separation of variables and solve it with integration, and you could get your c value in a different location. What we're looking at today, though, is going to deal with c being the initial amount, because we're dealing with the differential equation ky, which goes back to y equals ce to the kt. Now, normally, we would just memorize this equation and use that for anything where we know that the rate that the population changes is proportional to the amount present, which is y. But it is really good to know where that comes from, because that's the entire calculus side of it all. So what I want to do is show you how do they go from dy dt to this y equation. So they tell me that dy dt is equal to k times y. Where that comes from is they tell us in words that if a rate that the population is changing, where my population is y with respect to time, is proportional to the amount present, well, proportional means I'm taking k and multiplying it by something, where k is your proportionality constant. So it's proportional to the amount present, which is y, which is why we have k times y. Now what I want to do is actually solve this differential equation, which means I have to use separation of variables. So I have dy over y is equal to k dt. There's no need to move the k, I only need to put the y's on the left, t values on the right. So anything other than y can just stay on the right hand side. Then I'm going to integrate both sides now that I've separated the variables. The left hand side goes to ln absolute value of y equals kt plus c. Remember, you only need to put the constant plus c on the right hand side, because if you had one on the left, which technically you would have, you would just move it over and it would combine with the c value over here, so we only put it on the right hand side. Now I need to figure out what is this y actually equal to. So in order to get rid of ln, I'm going to raise each side to a power with e as the base. So then e to the ln cancels out, leaving me with the absolute value of y equals e to the kt plus c. In order to get rid of the absolute value, you just drop it and put plus or minus on the other side. But my goal is to get y equal to a big C e to the kt. And I don't quite have that yet, even though I have y isolated. So if you think back to algebra, whenever you have an exponential function where two parts are being added within the exponent, there was an algebraic property that said that that came from the first exponential to the first half times the same base to the second half. Because whenever you multiply with the same base, you would add the exponents. So basically I'm going to undo that algebraic step, and then notice I have e to the c. Well, e is a number, c is a number, this just creates a very big number. And so what I know is, if that's just a number, and then I have this plus or minus in front, this is an unknown number, because c is just a random constant right now. And so whenever this is just a random number, I can actually pull that out in front as a coefficient. So I'm going to pull out in front as a capital C, and that'll actually incorporate the plus or minus addition of that because C is a general term, a general number, and so because I don't know what it's equal to, it can just encompass that plus or minus inside this general term. So now I have capital C e to the kt left over, and that's my growth and decay equation that we're going to memorize for the calculus problems. But like I said, it's good to know where that equation comes from because that's the calculus side of it all. That deals with separation variables, with differential equations, so it's really good practice to know that. Plus, if they told me that a rate that a population changes with respect to time is proportional to something other than just the amount present, which was y, we would have to use separation of variables to actually solve for the solution, and that solution would no longer look like ce to the kt, it would look like whatever we have once we actually integrate and solve for the solution. So here's our first example. It says, suppose that a certain type of bacteria in a colony grows at a rate proportional to the amount present. The colony starts with one bacterium and doubles in number every half hour. How many bacteria will the colony contain at the end of the 24 hours? Okay, when you're reading this, you're looking for some key factors here. First key factor is, how is the rate proportional? And so that comes from the first sentence. It is a rate proportional to the amount present. That is telling you you are using the dy dt is equal to ky formula. Well, if I already know what that integrates back to, where it goes back to y equals ce to the kt, I can cut out the calculus step and go straight to that formula of y equals c to the kt, and I don't actually have to integrate to find the solution because I already know what the solution equation looks like. So what I need to do instead is figure out, okay, what are the pieces of this equation? So let's go back and see what else they gave us. So they said that we start with one bacterium and it doubles in number every half hour. So at time 0, my amount, which is y, at time 0 was equal to 1. And then it doubled in number every half hour. So the amount, which is y, at 0.5 hours is now double what we started with, so now we're at 2. And then my goal is to figure out how many bacteria will the colony contain at the end of 24 hours. So what is the amount at 24 hours? Now that I have those points, those are our initial conditions, which are going to help me find my c and my k value, so I can actually form the equation before I plug in the 24 hours. So working off of my equation, if I go with the initial condition of 0, 1, then the amount 1 came from times 0. Well, e to the 0 is just 1, so that tells me c is equal to 1. So remember, at the beginning of the video, I told you that c in these problems is going to be the initial amount. If you know that, then you can just start by plugging in your c value, which your c value would have to be 1. So I have 1 e to the kt. Now I need to figure out what is your k value, and that's why they gave you this second point over here. So I plug in 2 for y. K is still k, that's what I'm trying to solve for. Time is 0.5, because we're looking at y of t is equal to the y value. And so now I need to solve that for my k. So using algebra, I would take the ln of both sides, natural log of both sides, and then I would divide by that 0.5, and there's my k value. Now, even though we can type this in our calculator and get a decimal, we want to leave it like this, that way we don't have a rounding issue at the end. Because even if I go ahead and round it to 4 decimal places, just by rounding it, my answer is going to be off in the end by, it could be potentially a lot, because we're dealing with exponential functions here. So never round, never find the decimal until your very, very last step. So now if I rewrite my equation, I have y is equal to e to the k, which is ln of 2 over 0.5, times t, and I want to know what is the amount y at 24 hours. So then just go back and plug in 24 for your t value. And at this point, now you would go to your calculator and type that in. So typing that in, I get y is equal to 2.815 times 10 to the 14th. We're going to round to 3 decimal places. And my units here would be bacteria. So after one full day, 24 hours, you have a lot of bacteria. So definitely spreading very quickly. So that was an example of how you can actually see these types of problems with another subject, biology. You can also use it to find population changes, so another biology feature. There are a lot of other applications to growth and decay, and unfortunately I can't show you all of them today. But you can see this with finance and economics, if you're like looking at interest rates, things like that. The one we're going to look at next actually goes with chemistry. And so this one tells me, given the half-life of carbon-14 is approximately 5,700 years, how long would it take 50 grams of carbon-14 to decay to 42 grams? So just like the last one, we want to pick out the key features. Now we are assuming that the rate that the amount changes is proportional to the amount present. So I'm still using the same equation here. And so all I need to do is pick out the initial conditions that they tell me from the problem. So first of all, they say given the half-life is approximately 5,700 years. If you think back to chemistry, half-life is how long it takes for something to decay to half of the original amount. So this tells me the amount, which is y, at 5,700 years is going to be half of what we started with. Well, it told me that we began with 50 grams. So at the half-life, 5,700 years later, we will now have half of it at 25 grams. And then they also told me that we started with the 50, so I could write down that the amount y at time 0 is 50. And we're using these points with our equation for growth and decay to determine how long will it take for carbon-14 to decay to 14 grams. So a little bit different here. The last problem we were looking for the amount at the end of the time. This one is a little bit backwards. We are actually finding the time it takes to get to a certain amount. So I want to know the amount at what time, so I'm going to put a question mark right there, is equal to 42 grams. Now, still using the same equation, y equals CE to the KT. Remember, C is the initial amount, and so my initial amount is 50. So C would equal 50. And then I have to find the K value before I can actually find the rest of the problem. So in order to find the K value, I use the second initial condition that they gave us, the 5,700 and the 25. So y is equal to 25 when time is equal to 5,700. And of course you have to use algebra to find that. I would divide by 50, which gives me 0.5. Then to get rid of e, I would take the natural log of both sides. And to get k by itself, I would divide by 5,700. And again, we don't want to type it in our calculator and get the decimal. Keep it just like that. That way we don't have a rounding issue at the end. So then y is equal to 50e to the k times t. My goal is to solve for t when y is equal to 42, so I need to go back and plug in 42. And then it just becomes an algebra problem. So first step, if I'm trying to isolate t, would be I would divide 50 to the other side. And then I need to get rid of e, so take the natural log of both sides. So I'm not going to write every single step, but I have ln of 42 over 50 equals, the e is gone, ln of 0.5 over 5,700 times t. And then of course just divide what you have in parentheses here to the other side. Be careful typing it in your calculator, watch your parentheses. And once I do so, I end up with time is approximately 1433.771 years. So this is how long, in terms of years, it would take for carbon-14 to decay from 50 grams to 42 grams. Very long time for 8 grams to decay. Now, if you notice, this entire problem basically is just an algebra problem. There's hardly any calculus at all. All the calculus came from finding the equation y equals CE to the KT. But like I said, if you already know that dy dt is equal to k times y, it's proportional to the amount present, then you can just jump straight into the equation, and really there's no calculus. It's just plugging in numbers and solving for the unknown. So hopefully that helps you out. If it told you anything other than the rate being proportional to the amount present, you would have to set up an equation, separate the variables, find the antiderivative, then go from there by plugging in your points just like we did here. You would just actually have to find the antiderivative from the very beginning to have your solution equation. Thanks so much for watching.